So this is chapter 4 in which we study summary statistics. This is another branch of descriptive statistics, if you remember, in addition to graphical methods. Now remember, summary statistics you can do only for quantitative data, because when you calculate these summary statistics, you will be using the number properties such as addition, subtraction, like all kinds of arithmetic operations. Let me see, there is a typo here. Okay, so summary statistics are valid only for quantitative data. Okay, all right. So let's go to the next slide. Yeah, so the prior chapter had, the graphical methods. So in this chapter, we are using numerical summaries. Okay. All right. So now, when you talk about summary statistics, there are two types. Measures of central location. We talked a little bit about that even in the previous lecture or previous lesson. And then measures of spread. Okay. Now the shape summaries will not worry too much about this right now. We'll worry about central location and spread. Now there are three measures of central location. Central location means where is the data center. Okay. So you can use the you can use the mean, which is the average, median, which is the middle value, and mode, the number which occurs the most. Now for spread, how far out the data is going, you can use the range and the interquartile range, but they are not the best. And then of course you can use variance and standard deviation. Now in this chapter we are going to talk a good bit about variance and standard deviation, okay, as the measure of spread. So let's get started here with notation. Now we know that n stands for sample size. X is the symbol for the variable under consideration, any measurement, right? Now we will use the subscript I to say that, okay, xi is the specific value of the variable x for individual I. Now this is sigma notation. Sigma, capital sigma, in the Greek alphabet. This denotes adding. Okay. So now let's talk in terms of these numbers. So this is like x1. This is x2. See right here, x1 is 21, x2 is 42, and then these I values go from 1 to n. N equals 10 in here, so you will have x10 equal to 52. So now when you use sigma notation, you have summation xi. So that means this notation is like shorthand for adding. So what this means is you are adding from the first one, I equals 1, to I equals n, which is 10 here, and then you get 290. Okay? Alright, let's go to the next slide. So now, once you have the sum of the x values, you can find the sample mean, which is actually the average, and that is the traditional measure of central location. So you divide it by the sample size, and then the notation for sample mean is x bar. Okay. So now this is the sample mean. This is not the population mean. Now sample mean, once you have these observations, you can calculate. So sample mean is computable, but population mean is not. Okay, let me just write it in here. Sample Okay, so sample mean we can calculate because we have the sample at hand, but not the population mean because we do not have all the observations from the population. Okay, in fact, that is the idea behind statistics. we need to estimate things like population mean, which we do not know. And then sample mean looks like an appropriate estimate for the population mean. Okay. All right, let's go to the next slide. So here's an example. You can see, so 290, you need to divide by 10, and then you will get the sample mean to be 29. Now, if you look at that in a visual way, so 29 is somewhere here. It's sort of like the balance, it's balancing point where if you sort of put all the data, and if you put this, the X bar is the place where the data will not tilt either way. Okay. Now, sample mean, remember I told you that population mean is not known. So we can use the sample mean to predict the population mean. And, common sense can tell us that the sample mean is much better than a single measurement. Like if you think about, if you want to get the, let's say average income in Pennsylvania, if you take 1,000 people and then get the average income for based on that sample of 1,000 people, that is better than just picking just one person and asking how much do you earn, $25,000. So that's the prediction for the entire population in Pennsylvania. That's not good, just based on one person. But the sample mean would be much better. Of course, more observations there are, that estimate will be much better, for the population mean. So in other words, larger the n gets, sample mean will get closer and closer to the population mean. Okay, so now let's talk about the population mean. So now population mean, you can extend that formula of the sample mean to include all the observations and divide it by the total population size. Now the symbol for that is mu, the Greek letter mu. And see, typically, because we do not know this, we, in statistics, for the most part, Greek letters are used to denote the unknown quantities. Okay, so mu is not known. Okay, and then this mu, of course, I'll just say here, mu is not known. And that is what you expect the X value to take. So it is also called expected value of X, right? And then mu is, I'll just say, we will talk about this. Mu is an example of a population quantity, a population parameter. Okay, so any population quantity which we do not know is called a population parameter, and mu is an example. Okay, there we will come across others as well. Okay, all right. So now the next measure of center or central location is median. We talked about median even previously. So if you have, if you have n to be even, you will take like the middle value of the two middle observations. Okay, and then if n is odd, of course, you will take the middle value. All right. So that we know. Then let's go to the next one. Of course, when you have lots of observations, this kind of hand calculation is not feasible. We need to use a computer. I'm sorry. So these are some examples. You can go over them, or you can do them by yourself. Remember that always the observations should be ordered. That means ranked first. Okay. Now, one point about mean and median. Median is more robust if you have outlier observations. Now, here's an example. See, if you just calculate the mean for this, it's going to be 1636. Say by some chance, due to some mistake, 1 here is recorded as 9, and this becomes 9,867. If you calculate this, you will get the mean to be 2,743, much much more than the individual observations. And in fact, this is much more than the previous mean that you got. So now look, just because this value, this is actually outlier now. This is very different from the remaining observations. If you sort of do it on a x-axis, this will be very much away from everything else. So now mean got affected. But on the other hand, if you were to look at the median will remain the same to be 1640 with these data values and also with these data values. So median is more robust, mean is more sensitive when it comes to outlier observations or unusual observations. So typically what you should do is, if you want to be careful, you may want to calculate both mean and median both. And then if they are very much far apart, you sort of have to be a little bit alert and see, okay, are there any outliers? You need to look, okay? Okay, the third measure of central location is mode. Mode is the number with the highest frequency, okay? So now in here, if you look at, mode is 7. Here there is no mode, everything is occurring only once. Now, mode is usually only useful only in large data sets with repeated values. See, because if you do not have repeating values, it's not easy to find the mode. Now, I may mention something in here. Sometimes okay, now for large data sets, here's something you can do. You can say mode is the midpoint of the model class, okay? So now what is the model class? Where model class is the class with highest frequency. So that is actually the tallest class, right? So you can, this is sort of like an estimate. If you look at a histogram, look at the class which is the tallest and get the midpoint, that will turn out to be the mode, okay? All right, then let's go here. Okay, now remember we talked about symmetry and then skewed distributions. Now if you have a symmetric distribution, mean, median, mode, all three measures of location are going to be on the same spot. Okay, they're all equal. If you have positively skewed, the mode will be more to the left and mean will be more to the right. And then negatively skewed, it will be the other way. Okay, so these are just things to remember. I mean, you don't have to memorize these, but just keep in mind that there is a relationship between skewed distributions and the locations for mean, median, and mode. Okay, all right. Now the next one is, remember now up to this point we talked about measures of location. Next one is measures of spread. Okay, now you can have data sets or data distributions to have the same mean, but their spread would be very much different. Now in this data set, they have calculated both data sets to have mean 36. Now this is like a double stem plot. See, there are observations coming from site 1 and site 2. So if you look in these middle values, see this vertical, the numbers in between the vertical strokes, they are the stems for both these stem plots. Okay, there is this right side stem plot coming from site 2 and the left side coming from site 1. So for comparison reasons, they have put them together. And then if you look in here, but when you calculate the mean will be the same, which is 36. But there's going to be, look, it's not the same spread here. Look, in the right side, the largest or the maximum value is 40, whereas on site 1, the maximum value is 68. And then here the minimum or the smallest is 32. So the range here is going to be from 30 to 40. So small. It's a very small range. And here the range is going to be from 22 to 68. Okay. So though they have the same mean, the spread is so different. Okay. So actually now if you were to calculate, look, site 1 range is 64 as we saw, and site 2 range is 88. Such a big difference. And then also, this range is not very good because typically we will calculate the sample range, and sample range will, you can sort of guess at this, it's going to underestimate the population range because you will just take a bunch of numbers for the sample, but population could have lots of numbers way out on either side. Okay. So because of that, if you give the range, you need to supplement it with another measure of spread. Remember, we talked about the interquartile range and also the standard deviation. Okay, so now let's see. So now quartiles. Now quartiles are the 25th percentile, that is the lower quartile, and the 75th percentile, which we talked about, that is the upper quartile. Okay, and then interquartile range is the difference between the upper and the lower quartile. Let me write it here. Actually, Q1 is also called the lower quartile. And Q3 is the upper quartile. Because upper quartile, the boundary for the upper quartile, upper fourth is Q3, upper quartile. Okay. Now, so if you use the same reasoning, actually Q2 is the median, but hardly. But it's not, people don't use that. People don't use Q2 as the median. Okay, rarely used. Okay, all right. So now here's the median, which is actually the 50% mark. So Q1 is the 25th, then you have the 75th. So interquartile range would be 42 minus 21, which is another 21. Okay, all right then. So yeah, so in fact, they tell another thing to do. Another way to calculate the quartiles is you first find the median, then you divide the data into the bottom half and the top half, and then if you take the bottom half and if you find the median of that, that's going to be the lower quartile, and the median of the upper half is going to be the upper quartile. Okay, so Q1 and Q3 you can find that way as well. Okay, just another way of finding Q1 and Q3. Okay, so let's go. Which one am I in here? Okay. Okay, now, so if you have a data set, these are 5 things that are useful in sort of giving the spread of the data. Q0, which is the minimum, Q1, which is the 25th percentile or the lower quartile. Let me write it here. Quartile, and then Q2 is a median. It's, Q2 is used here, or this is upper quartile, and then Q4 is the maximum. So if you sort of report this, the user can make sense of it, how the data is spread out. Okay, all right. So let's see. Now, in addition to 5-point summary, to get an idea of the spread of the data, there are these box plots. That's actually a um, visual tool. Now, this is how you do the box plot or construct the box plot by hand. But let's not worry about that, because any computer software will give us the box plot. So let's look at that and see how we can interpret this. So this is what the box plot is. Now here the data is like this is like the data axis. Now right here, this value is the median. This horizontal line is Q2, that is the median. Now this is actually the box. The boundaries of the boxes are the Q3 and Q1, and so actually the dimension or the height of this box is the interquartile range, Q3 minus Q1. Okay, and then you have something called let's see, these are called whiskers. Okay, now any observation outside the whiskers are considered to be outliers. That's what I have mentioned in here. So if you have a box plot, these two are Q3 and Q1. So you can find the interquartile range. This line represents the median. These are called whiskers. Okay, I think I mentioned that in here. Any number outside the whiskers are considered to be outliers. Okay, all right then. And then yes. So let's go to the next one. I think there's another example here. Yeah. So now the 5-point summary in that sense would be, so you start with the smallest, which is 3, and then you have Q1. Let's see, Q lower hinge is 22, Q1. Then you have 25.5, which is the median. Then you have 29 right here, and then the maximum number is 51. But see, notice here you have the whiskers. These two observations are outliers because they are outside the whiskers. Okay. Now this data set is, it's really pretty good. Actually, the spread is not as bad at all. And look, the median is right here, and this seems to be quite symmetric also. The portion above the median and below the median inside the box is pretty similar. Okay. Okay, so let's go here. So another example, you can see this is the median again. Now in here there are no outliers. You can go over them a little bit more. Just to get an idea. Yeah, so now as we talked, the position of the median and the position of the box, that tells you the location. If the median is like right in the middle, then that means the data is in fact symmetric. And then IQR, the whisker to whisker spread, and the range gives us an idea of the spread. And then of course the shape is, in terms of symmetry. Like if the median is right in the middle, that you can sort of think that the data are symmetric. Okay. Okay, so we did that, and then let's go here. Now another useful thing in box plots is to, it can be used to compare two data sets. Now here you have two groups A and B. Look, group B, the mean or the median is so much bigger than the group A median. So, you can say that. And also the spread. See, the spread of course is more in here. That's not a good thing. This is actually here the data is much tighter, which means the data is pretty good. But here the data is more spread out. Okay, the median here is more than the median in this group. So for comparisons, this is box plots are really good. Okay, so the last subtopic for this lecture, standard deviation as a measure of spread. Actually, this is considered to be the most common descriptive measure of spread, just like the mean is the most common descriptive measure for center, measure of center. Okay. Um, Now, standard deviation. In standard deviation, what you do is you take the deviations of each observation from the mean. Okay, so I think the next slide has a diagram here which shows what's happening. So here you have the mean. Remember, the notation for mean is x bar, and then you will have individual observations, which are these blue dots. So to get the deviation, you need to subtract the mean from each deviation. Okay, so like for example here, 40 minus 36 will give you 4 to be the deviation for x equal to 40. Likewise, 32 minus 36 is negative 4. So remember, the sign matters. See, the observations which are to the left of the mean will have negative deviations. Okay. So now, if the data is very spread out, the deviations will be spread out as well, right? Now, to get one unique measure, see, if you have n observations, there will be n deviations, but you need to sort of summarize it into one measure. So in order to do that, one good way would be to get the, to sum the deviations in one way. Okay, so let's see what happens in the next slide. um, so let's first of all learn a little bit about the notation. So deviation would be xi minus x bar. This is like the ith observation. And then instead of, see now, one way would be to average the deviations. But see, when you average the deviations, you will have to find the sum of the deviations, not the square deviations, just plain deviations. But see, think a little bit here. There are plus deviations and minus deviations. Now, see, mean is the average. So what happens is, if you add all the deviations, the plus deviations cancel out the minus deviations, and the average, or the sum actually, will add to 0. So always the average deviations for a sample will turn out to be 0. So it's meaningless. So because of that, to avoid that problem, only the the each deviation is being squared. When you square each deviation, the distance part remains. If you have an observation to be very much away from x bar, this deviation will be very large. So will be the square. So that distance or the magnitude of the deviation will be preserved. Only thing is the sign will be lost. It's okay. And then, once you add them all up, this will be a good measure for how spread out the data is. And then now, to average it out, typically you need to divide it by n, but due to a statistical reason, you will divide it by n minus 1. Okay, I'll just write it in here. If you do a more advanced stat course one day, you will understand why you divide by n minus 1 uh, instead of n. Okay, so let me just write it down here. Divided by n minus 1 instead of n for a statistical reason. Okay. Okay, so once you have that, now this is, remember, or look in here, these are squared values. So if you have x to be in inches, deviation will be in inches, squared deviations will be in squared inches. So this is actually, and then notation wise, they develop the notation so that this quantity is called s squared, and that is given the name sample variance. But see, this is like, even if you think in terms of inches, s squared is in squared inches. Okay, squared inches you cannot mark on the inch axis, right? X is, if you have x's in the units of inches. Okay, so you need to put this back into inches, or the units of x. So to do that, you square root, and then that square rooted measure is called the sample standard deviation, and notation is S. So you have S to be the sample standard deviation, which is the standard measure of spread, and X bar to be the sample mean, which is the standard measure for location. Okay, so those are the two important quantities that you need to remember as summary statistics. Those are the two most important ones: X bar, excuse me, X bar and S. Okay. So here's the standard deviation formula, and then now we need to bring in the population standard deviation. Remember, we talked about population mean mu, and then we said that the X bar, which is a sample mean, estimates mu, which is not known. Likewise, the population standard deviation. In other words, if you take deviations from all the observations in the population and divide by uppercase n minus 1, then you will get, and you square root it, you will get population standard deviation. Now that is denoted by the Greek letter sigma. Okay, this is the Greek letter sigma. Okay, so sample, not sample, population standard deviation is denoted by sigma, another Greek letter. This is of course the lowercase. Remember that summation notation was uppercase, sigma. And then so you can say, I can say actually S estimates sigma. And why should we estimate sigma? Because we do not know. This sigma is also there. Sigma is an unknown population parameter. See, this is another example of a population parameter, just like the population mean is. Okay, so now we learned two population parameters, mu and sigma, and they are being estimated by their sample counterparts, X bar, which is a sample mean, and S, which is a sample standard deviation. I'm talking a lot about this because these are very important. X bar and S and mu and sigma are really very important. Okay, almost all the statistical procedures that you'll be learning later will involve X bar and S and mu and sigma. Okay, all right, so here they have an example of how to get it. If you have calculate this the sample standard deviation, I mean, if you like, you can go over it. It's really not a big deal. We will be using software to calculate such. Okay, so these are the formulas, and in fact they applied it for that data, and then you get the answer. If you like, it won't take that much time, not even 5 minutes. You can try it yourself. Okay. Yeah, okay, so now interpretation of standard deviation. Now there are certain rules. Now this is 68, 95, 99.7 rule. Actually, it is called, that first one is more commonly known as 95 to 99.7 rule is actually called the empirical rule. Because see, these figures 68, 95 and 97 have been worked out by looking at just data. That is why it's called empirical. It's not proved mathematically, but empirically it is evident. Okay, let me correct the spelling here. Okay, empirical rule. Okay, so let's go to the next slide. So then this is actually this is for empirical rule. You can say I mean, the book says it's only for normal distributions. We have not done normal distributions yet. Uh, I could say mound shaped distributions. I mean, I'll just put that in here. We have not still done it anyway, so let's see. Oh, I'll just take that and then say mound shaped. So if you have like a mound shaped distribution, which is like a bell shape, of course, typically it's a normal distribution. Um, you can say that 68% of the data will be in the range of mu and sigma on both sides. And then 95% will be within two standard deviations. 99.7, that means like almost all, will be between three standard deviations. Okay. So that's what it says. So actually, based on this, you can even figure out what the minimum value is and the maximum value. Minimum is mu minus 3 sigma, right? Minimum value is approximately mu minus 3 sigma, and the maximum value is mu plus 3 sigma. Okay, so this is a good rule to remember, and it is called the empirical rule. Now, the next one is Chebyshev's rule. Now, the Chebyshev's rule applies to any distribution, but let's not worry about that. We don't really need that, okay? And then we don't need this. Yeah, this is like a good way to, report summary statistics for a data set. Always report a measure of central location, a measure of spread, and the sample size. So if the data is symmetric or mound shaped, report the mean and the standard deviation. If you have an odd shaped distribution, report the 5-point summary. Okay. So this is just like a rule of thumb. Okay. And anyway, it's a good rule of thumb. And then you can always use software to calculate all these summary statistics, mean, median, the percentiles, everything. Okay. So we are blessed that way right at this point. It's not like 30-40 years ago. Okay, so we are done with chapter 4, and then we need to get into chapter 5 after this. Okay, so if you have any questions, please email me and then discuss among yourselves also. Okay, take care.